just wait for 2 minutes to see if someone is joining, then we will start. I think we'll just start. So today is the week 7 of the live interact of the NPTEL course, Introduction to Atmospheric and Space Sciences. So last class we were mostly discussing about different moisture parameters. We also learned what is meant by saturation and also different types of temperature like dew point temperature, wet bulb temperature, equivalent temperature. Also we learned what is potential temperature, how to derive the temperature and all those things. So today we will start with solving one or two problems related to the dew point temperature, and then we will learn some new terms like pseudo-adiabatic process, lifting ionization level, level of deconduction. So just to revise, last class we told that last class we were talking about saturation. So saturation basically means the air parcel holds the maximum amount of water vapor it can contain. If we add more water vapor to it, then basically it will undergo condensation because it has exceeded that maximum amount of vapor that it can contain. We also learned that the saturation vapor pressure is a function of T, which is basically represented as ES, as a function of temperature, which is given by A e raised to minus B by, where A is having a value of 2.53 into 10 raised to 11, and B is having a value of 5420 Kelvin. T is the temperature. So we also learned saturation vapor pressure is basically a function of temperature. And we learned there are, for an air parcel to become saturated, there are two ways in which it can be saturated. One way is keeping R constant, which means the mixing ratio of the parcel is not changing. But if we reduce the temperature, the capacity of the air parcel to hold water vapor decreases, and it will eventually become saturated with the actual amount, with water vapor amount it had initially, without adding more water vapor. So if we reduce the temperature of the air parcel, it will eventually become saturated. So that temperature we got was dew point temperature. The temperature that the parcel will reach once it becomes the temperature up to which the parcel should be cooled for the parcel to become saturated. That was dew point temperature. We also learned another way, which was by increasing the R. R, if you remember, is mixing ratio, which is given by mass of water vapor to mass of dry air. So another way is by increasing the mixing more water vapor to the parcel. So this was another way, and then we learned like when we talked about adding more water vapor to the parcel, we learned another type of temperature which was wet bulb temperature, which is basically measured using the wet bulb thermometer. It is different from dry bulb thermometer because it has a moist cloth which is covered to the mercury bulb on the bottom of the thermometer. So basically, this by evaporation of water moisture content from the cloth to the air parcel close to the thermometer, the parcel will eventually become saturated. So during the conversion of the water from the moist cloth to the vapor, which is being added to the parcel, there happens evaporation. So there will be an absorption of energy, which is basically latent heat of which is equal to the latent heat of vaporization, which is basically provided by the air parcel itself. So since air parcel is providing that energy, the air parcel will eventually cool as more and more water vapor is added to the parcel. So that temperature that eventually the parcel will reach once it is saturated is known as the wet bulb temperature. So we learned TD, which is the dew point temperature. In this case, the mixing ratio is kept constant. And another one we learned, which is wet bulb temperature. In this case, we are adding more water vapor to the parcel, and then the temperature that the parcel will eventually reach when it becomes saturated. That is wet bulb temperature. So these two things we learned last class. So we will just see how can we derive how can we reach an equation in which we can calculate the dew point temperature. We will derive an to calculate the dew point temperature. So as I told, we already know the saturation vapor pressure is given by the equation Es of T is equal to A raised to minus B by A. So suppose when a parcel becomes saturated, it means its actual vapor pressure is equal to saturation vapor pressure. Its relative humidity is equal to 1, and the temperature will be T will be T. So if we substitute E is equal to Es and T is equal to TD in the above equation, or let us say equation number 1. In equation 1, it will become E of T is equal to A raised to minus B by TD. We substituted E instead of Es and TD instead of T. Now if we take the logarithm on both sides, it will become log E is equal to log A minus B by dt. Now B by dd becomes log E or log A minus log, or we can write B by dd is equal to log A by, finally dd becomes B by log A by E, where E is the saturation vapor. Now we know that the vapor R is basically mixing ratio in terms of vapor pressure. We can write it as R is equal to epsilon into E by T. The vapor pressure divided by the pressure of dry air. So from this we can write E is equal to P into R divided by epsilon. So if we substitute E in this equation, it will become TD is equal to V by log of PR by epsilon. A is also A PR A We have to substitute 1 by E is equal to PR by epsilon. Here we have 1 by E, so it will become A epsilon by R into. So this is the equation for dew point temperature. TD is equal to V by log A epsilon by R into. From this, we can say that the dew point temperature TD is the function. Here if we look, V is a constant, A is a constant, epsilon is a constant which is given by R d by Rm. The specific gas constant before dry air by moisture. That ratio is basically epsilon. So TD, V is constant, A is constant, epsilon is constant. So TD is basically a function of mixing ratio and the pressure at which we are calculating the dew point temperature. So TD is basically a function of mixing ratio, that is the amount of water vapor present in the parcel and the pressure level at which we are calculating the dew point temperature. Okay, I think it is clear. So the dew point temperature TD is given by V by log A epsilon divided by R into V, where R is the mixing ratio, pressure is the level at which we are calculating the dew point temperature, epsilon is constant, which is RT by Rm. Now let's solve an equation with this equation. So, question is calculate the dew point temperature of an air parcel which has mixing ratio R is equal to mixing ratio can be R as both R and W. So if you see the notation W, that is also R is equal to 22 gram by kilogram, and if the cell is at pressure levels, first one is at the pressure level P1 of 850 hectopascal, then 2 that is at a pressure level of 700 hectopascal, then 3 that is at a pressure level P3 of 500 hectopascal, and R is constant. 22 gram by kilogram. Okay. Now what is the equation that we just learned? We learned TD is equal to V by log A into epsilon by R into P, right? So we know what is the value. So this is the first case when P is equal to 850 hectopascal. P1 is equal to 850 hectopascal. So we know the value of B is 5420 Kelvin. The value of A is 2.53 into 10 raised to 11. The value of R is given as 22 gram per kilogram. If we convert it into SI unit, it will be 0.022 kilogram per kilogram. Then the value of P in the first case is given as 850 hectopascal or 850 into 10 raised to 2 pascal. So while substituting, you have to convert it into pascal and then substitute. So TD will become 5420 divided by log of 2.53 into 10 raised to 11 into epsilon. The value of epsilon is RD by Rm, which is 0.622. 0.622 divided by the value of R is 0.022 into P. P is 850 hectopascal or 850 into 10 raised to 2 pascal. So can you calculate and tell me what will be the value of dew point temperature at the pressure level 850 hectopascal? 5420 divided by log of A into epsilon divided by R into P. Did you get how much it is coming? Yeah, 297 Kelvin. So the answer will be 297 Kelvin or 24 degrees Celsius. So an air parcel which is at a pressure level of 850 hectopascal having a mixing ratio of 0.022 kilogram per kilogram has to be cooled to a temperature of 24 degrees Celsius to reach saturation. Now let's see the second case when it is at a more higher pressure. So the second case, here the pressure level is 700 hectopascal. The method is the same. You just have to substitute 700 instead of 850 in the earlier case. So it will be 5420 divided by log of 2.53 into 10 raised to 11 into 0.622 divided by omega or R is basically 0.022 into P. Here in this case it is 700 into 10 raised to 2. How much it will be in this case? At pressure level 700 hectopascal. Same thing, just replace the pressure, the value of pressure. So in the second case, how much it is coming? And the pressure is changed from 850 hectopascal to 700 hectopascal. Parcel is basically raised from a lower height to a higher height at 12 over pressure. So how much it will come? What is happening to the temperature? 293. So in this case, the temperature is becoming 293 Kelvin or 20 degrees. This is the temperature to which the parcel needs to be cooled when the parcel is present at a pressure level of 700 hectopascal. Now the third case, when the pressure level is 500 hectopascal, repeat the same thing, just replace P by 500 hectopascal. How much it is coming in this case? Now the third case, when the pressure is again reduced, or the air parcel is further lifted to a height of 500 hectopascal. How much is the dew point temperature? Yes, 288 Kelvin. 288 Kelvin, which is 15 degrees Celsius. Now we compare the dew point temperature at three different levels. It is coming as the dew point temperature at the pressure level. We found out it was 24 degrees Celsius. 24 degrees Celsius. Second case, we found out it was 20 degrees Celsius. And in the third case, when the pressure was 500 hectopascal, the temperature was 15 degrees Celsius. So the TD at pressure level 1 is greater than the dew point temperature at pressure level 2 is greater than the dew point temperature at pressure level 3. So which basically means that as the pressure is lowering, as we go up in the atmosphere, the temperature that the parcel should reach to attain saturation is also decreased. But if we look at, we also have to consider the temperature at the actual temperature at these pressure levels as well. We know that as we go up in the atmosphere, the temperature is reducing. The temperature is reducing with height in atmosphere. So, like according to DLR, we calculate the dry adiabatic lapse rate, which is around 9.8 Kelvin per kilometer at 500 hectopascal level. Dew point temperature is there will be an actual temperature for the parcel. So from the actual temperature, how much it should be cooled so that it will reach saturation. So we should know how much is the temperature at a 500 hectopascal. Similarly, like at 500 actual temperature at 500 hectopascal or 700 or 800. So at 500 hectopascal level, we can calculate. We don't know what is the value of Z. So we can calculate Z from delta P by delta Z is equal to minus rho G. So delta Z we can write it as delta P by rho into G. So delta P is 500 into 10 raised to 2 by rho will be 1.032 into what will be the height at pressure level 500 hectopascal. 500 into 10 raised to 2 is equal to 1.032 into 9.8. It will be around 4,943 meter, approximately 5 kilometers. So when we are telling at a level of 500 hectopascal, it basically means at a height of 5 kilometers. So at the height of 5 kilometers, what will be the temperature according to the dry adiabatic collapse rate? So dry adiabatic collapse rate dT by dz we know is 9.8 Kelvin per kilometer. So at a height of 5 kilometers, suppose if the surface temperature is 30 degrees Celsius, how much it will be at the height of 5 kilometers? The surface temperature T is 30 degrees Celsius. At the height of 5 kilometers, the temperature will be, as it moves every 1 kilometer, it is reducing by 9.8. For every 5 kilometers, it is reducing at this rate. So at the height of 5 kilometers, the temperature will be lower. So compared to the actual temperature, it should be reduced by 15 degrees. From that temperature only, it needs to be reduced by 15 degrees Celsius. So since the actual temperature itself will be lower at these particular levels, then it will be more easier. It is not like from at higher levels, since the actual temperature itself is lower, it will be easier to reduce the temperature to 15 degrees Celsius. That was the whole idea I wanted to. So that is dew point temperature. Now let's solve another question. Which is, if the temperature of a parcel at 700 hectopascal is 10 degrees Celsius, what is its saturation mixing ratio? The temperature of a parcel at 700 hectopascal. At pressure is equal to 700 hectopascal. The temperature is given by 10 degrees Celsius or 283 Kelvin. Now we have to find ES. We know ES. Now we have to find RS. ES. We need to find RS. So RS is saturation mixing ratio is basically given by epsilon into ES by P. And ES we know is A raised to minus B by P. So if we substitute, we can write RS, or saturation mixing ratio, is epsilon into A minus B by P, the whole divided by pressure. So it will become 0.622 into 2.53 into 10 raised to 11 into E raised to B is having a value of 5420 divided by temperature is 283 Kelvin, the whole divided by the pressure 1100 into 10 raised to. Can you tell me how much is the saturation mixing ratio? What will be the saturation mixing ratio of the parcel? How much amount of water vapor should be there in the parcel for it to become saturated at a temperature of 10 degrees Celsius and at a pressure level of 700 hectopascal. how much it will be? What will be the saturation maximum ratio? Yes, the value is around 0.01. So the answer will be 0.011 kilogram per kilogram. Or we can write it will be, it is basically kilogram, so we can write 11 gram per kilogram. So for 1 kilogram of dry air, 11 gram of water vapor is required for this air parcel to become saturated. So yeah, that is the whole idea. Now let's see. So we are assuming all atmospheric processes to be adiabatic. That is, no heat is being added or released from the system. So now there is something known as pseudo adiabatic process. So we are considering most of the process in the atmosphere is adiabatic. So there is something known as pseudo adiabatic process. Let's see what does it mean. So before that, I think I had discussed this topic of lifting condensation level. I would have just introduced the term lifting condensation level in the last class. So lifting condensation level, it is the level up to which an unsaturated moisture parcel must be raised The lifting condensation level is the level up to which an unsaturated moisture parcel must be raised so that the parcel reaches saturation. So as we saw earlier, as we go up in the atmosphere, the temperature to which there are different temperature in each layer when the parcel is supposed when the parcel will reach saturation. It was different at each level. So and also as we go up in the atmosphere, the temperature reduces as well. So one way of reducing the temperature of an air parcel is to lift the air parcel along the, or if the atmosphere is lifted in the atmosphere, eventually the temperature of the parcel will reduce, and at some particular level it will reach a temperature at which the actual temperature and the dew point temperature will become equal. So that particular level in the atmosphere at which the unsaturated moisture parcel will become saturated is known as lifting condensation level. So once the parcel is saturated, if we further lift the parcel, since the parcel is, so we at lifting condensation level, the atmosphere, we consider, suppose this is the actual temperature profile, which means the how the temperature is reducing as we go up in the atmosphere. We know that the temperature reduces as we go up in the atmosphere. This is the actual temperature profile of the atmosphere. So there is a parcel which is being lifted in the atmosphere. So as we lift the parcel in the atmosphere, the temperature of the parcel will reduce according to dry adiabatic lapse rate (DALR), and at some particular point the parcel will become saturated (LCL), and the actual temperature of the parcel will become equal to dew point temperature, which is the temperature required for the parcel to become saturated. So at some particular point it will reach LCL or lifting condensation level. So if we further lift the parcel up in the atmosphere, if the parcel is further lifted, what happens is that the temperature will further reduce. So if the temperature will further reduce, the parcel is already holding the maximum amount of water vapor that it can hold. So if we further lift the parcel, that level will exceed. So it can no longer hold the water vapor that it already has. So what will happen? It will start condensing. Since the parcel is already saturated, so if we raise the parcel above the lifting condensation level, what will happen? The parcel will try to expel the additional water vapor that is present, or we can say the parcel condensation will start to occur in the parcel. Condensation will start. So at the LCL, the parcel has already reached saturation. Now if we further lift the parcel, the temperature of the parcel will be further reduced. It can no longer hold the amount of water vapor that it already has. So it will start condensing. So once it starts condensing, water will be formed. So we can say cloud formation. Cloud formation starts. So LCL is generally considered as the base of the cloud. So what I was telling, suppose this is the atmospheric height in the atmosphere, and this is the temperature. So there is a parcel which was at the surface. By some mechanism, the parcel was lifted. So as it is lifted, the temperature will keep on reducing, and at some particular level, the actual temperature of the parcel and the dew point temperature of the parcel becomes equal. T will become equal to TD. That particular level is known as lifting condensation level. And if we further raise the parcel in the atmosphere, we know that it is already saturated. So if further the temperature will reduce, it can no longer hold the water vapor that it already contains. So condensation will start to occur. Gradually cloud formation will start. So basically LCL is the base of the cloud. I hope it is clear till now. Now since condensation starts occurring, so condensation basically means whatever water vapor is present in the parcel is condensing and water is formed. So since condensation starts occurring, latent heat of condensation will be released. During the conversion of vapor to water, there will be release of latent heat. So above LCL, condensation starts, which basically means water vapor will start condensing to water. So there will be release of latent heat of condensation. So this latent heat of condensation will be used to or this will be added to the parcel. Basically the parcel the latent heat of condensation increases the parcel temperature. So even though as it is above LCL, the parcel is moving. Um, the parcel is moving up. The value of dt by dz will be less than the value of dt by dz before LCL, because after LCL condensation is occurring. So as we go up in the atmosphere, there will be the reduced in temperature which is given by dt by dz, and as it is decreasing, there will be an additional amount of heat that is being added to the parcel in the form of latent heat of condensation. So the rate at which the temperature reduces as it goes above LCL is less compared to that, um, or compared to the rate before LCL. So the value of dt by dz will be, the rate of decrease in temperature will be less compared to that of the rate of decrease in temperature before LCL, because there is an additional amount of heat that is being supplied to the parcel due to the condensation of water vapor within the parcel, which is basically the latent heat of condensation. And since this uh, water, whatever is formed within the parcel, it will precipitate out. So we assume that whatever water is being formed within the parcel is precipitating out. So in this case, some part of the some matter or some amount of material is leaving the system, which can take some of the heat within the system as well. So in this case, some heat or some amount of matter is actually leaving the system. So now the process is no longer adiabatic. Once precipitation starts or after condensation, if the formed water droplets or water molecules are leaving the system, then the process no longer is adiabatic. Instead, we call the process as pseudo adiabatic. So above LCL, condensation starts to occur. There will be latent heat release, and water will be formed. Vapor will convert into water, and these water will leave the system, carrying some amount of heat along with it. So now the process is no longer adiabatic. Instead, it is known as pseudo adiabatic process. And one more thing that to be noted is that above LCL, the rate of decrease of temperature with respect to height will be less than compared to that of before LCL, because there is an additional amount of heat that is being supplied to the system through the latent heat of condensation. Okay, I hope it is clear till now. Now, when we discuss the dry adiabatic collapse rate, dry adiabatic collapse rate, it is basically for dry air passes which doesn't have moisture content. So here in this case we are considering moisture parcels, which means moisture parcels. This has some amount of water vapor in it, even though it is unsaturated. Completely, it is not completely dry. It has some amount of water vapor in it. So in that case, the lapse rate is known as moist adiabatic lapse rate. So till now, the term that we learned, or the term that we have been using, is known as the dry adiabatic lapse rate, which is applicable for dry air parcel in which there is no moisture content in the parcel. But here they are considering air parcels which are moist, which means even unsaturated, it has some amount of water vapor within the parcel. So let's see how we can derive the equation for moist adiabatic lapse rate. We know the equation for dry adiabatic lapse rate, or gamma d dt by dz in case of dry air, or dry adiabatic lapse rate, is given by minus g by c. Now let's see what is the value of gamma n for an air parcel which has some amount of water vapor in it. Moist adiabatic lapse rate. We will see what is this. we will start with the first law of thermodynamics. So we are going to derive the equation for moisture adiabatic reaction. So according to first law of thermodynamics, we know dq is given by Cp dt minus alpha d. So this is the first law of thermodynamics in terms of specific heat at constant pressure. If you remember, we learned three or four different forms of first law of thermodynamics, which had the basic form dq is equal to du plus dt. So dq can be written as Cp dt minus alpha for adiabatic process, since we generally consider most of the processes in the atmosphere to be adiabatic in nature. So for adiabatic process, dq is equal to 0. Or we can write Cp dt is equal to alpha d. So according to first law of thermodynamics, dq is equal to Cp dt minus alpha dt. Now if we are considering adiabatic process, dq can be written as 0. So Cp dt becomes alpha dt. Now from hydrostatic equation, we know dt by dz is equal to minus rho g. Now if we substitute, or we can write, we know T is equal to rho RT. Rho is basically 1 by alpha, or T is equal to RT by alpha. P alpha is equal to alpha. So dt by dz can be written as minus g by alpha, or alpha dt is equal to minus g. Okay, this is not coming, just the rho is equal to, just substitute rho is equal to 1 by alpha. So from hydrostatic equation, we know dt by dz is equal to minus rho g. Basically, rho is basically 1 by alpha. So dt by dz can be written as minus g by alpha. And then it will further reduce to alpha dt is equal to minus g dz. So let this be equation 2. And the first law of thermodynamics that we wrote, Cp dt is equal to minus Cp dt is equal to alpha dt is equation 1. So from this we can write, earlier we wrote Cp dt is equal to alpha dt. dp from first law of thermodynamics. From these two we can write Cp dt is equal to minus g dz, and dt by dz is equal to minus g by Cp. So this is the equation for, this is how we derived the dry adiabatic gas, right? dt by dz is equal to minus g by Cp, minus 9.8 Kelvin per kilometer. Now in case of moisture, dt by dz will become minus g by Cpm, which is the specific heat constant for moist air. Just like we have Rd and Rm, but Rm basically depends on the amount of moisture present in the particle. Similar like that, we have specific heat constant that dry air as well as for moisture. So this is the equation in case of moisture. dT by dz for moisture minus G by Cpm. So what is Cpm? The specific gas constant for moist air, which is unsaturated but has some amount of moisture in it. Suppose you have 1 kilogram of dry air which has R or mixing ratio R, let's use W in this case instead of R. So mixing ratio, the notation of mixing ratio can be R or W. Both are used. So let's use W in this case. So suppose 1 kilogram of dry air has a mixing ratio of W. Like W amount of water vapor is present in 1 kilogram of dry air. So we can write the first law of thermodynamics can be written in this form, which is 1 plus W dQ is equal to Cp dt plus W into Cpv dt. So in case of moisture, it will reduce to the first law of thermodynamics we can write in the form 1 plus W into dQ is equal to Cp dt plus W into Cpv dt. So Cp is a specific gas constant for water vapor. And W gives the amount of water vapor in the vessel. So based on that, we will determine Cpm. So Cpv is for solely for water vapor, and Cpm is for a moisture vessel which contain dry air and some amount of. So we know the Cp, what, like the specific gas constant can be written as dQ by dt. So we can write dQ by dt is equal to Cp into, this is dQ, right? Cp into, if we divide dt in this equation, if we divide this whole equation by dt, it will become dQ by dt is equal to Cp into 1 plus W into Cpv by Cpd divided by 1 plus W. So we divided the whole 1 plus W into dQ is equal to Cp dt plus W Cpv plus dt. The whole equation was divided by dt so that we will get Cp. Cpm is basically dQ by dt. So if we divide the whole equation 1 by dt, we will get dQ by dt is equal to Cp into 1 plus W Cpv by Cpd or Cpd into 1 plus W Cpd by Cpd divided by 1 plus W, where W is the mixing ratio. Now we can write dQ by dt is equal to Cpd into 1 plus W into R. So this value Cpd by Cpv is another constant which is denoted by R, just like our epsilon, which is given by Rd by Rn. This is another constant which is Cpd by Cpv. 1 plus W into R divided by 1 plus W. So in this case W is mixing ratio. So it will be Cpm, dQ by dt is basically Cpm is equal to Cpd into 1 plus 0.9 into W. The value of R is given by, so Cpd will reduce it into Cpm is equal to Cpd into 1 plus 0.9 into W after substituting the value of R. So we can write the lapse rate for by dz we wrote as minus G by CPM, which is specific heat for moisture. So we just got the value of specific heat of moisture. So dT by dz in case of moisture parcel, which has some amount of water vapor in it, but it is still unsaturated. It will become minus G by CPD, which is the specific gas constant at for dry air. The value that we know 1 plus 0.9 into W. For W is the mixing ratio. Or you can write R as instead of so minus G by CPD into 1 plus 0.9 into I. So that is the final equation. R is basically having a value of 0. CPD by CPD is having a value of 0. So minus G by CPD to 1 plus 0.9 into W. So this can be further reduced to, so we just got dT by dz for moisture parcel, which is gamma m is equal to minus G by CPM, which is a specific gas constant, specific heat constant for moisture. And we just found the value of CPD, which is CPM, which is CPD into 1 plus 0.9 into W. Let's write R. R is the mixing ratio. So gamma m will become G by CPD is dry adiabatic lapsing that we are already familiar with, minus gamma D into, if we expand this, which is 1 plus 0.9 the whole raised to minus 1 in terms of binomial expansion, we will get, if we only take the first term, it will be minus gamma D into 1 minus 0.9 into R. We already know the value of R, which is 9.8 into 1 minus 0.9 into, this will be the value. So let's do a problem. I think it is clear. So we are already familiar with the term dry adiabatic lapse rate, which is the rate of decrease in temperature with respect to height in case of a dry air parcel. So we were trying to find what is the value of the lapse rate when we are considering a moisture parcel which contains water vapor but it is still unsaturated. So we know the value of dry adiabatic lapse rate is G by Cp. So in case of moisture, it will become G by Cpm, where Cpm is a specific heat constant for moisture. Then we found the value of Cpm, and after substituting it, we got the moisture adiabatic lapse rate as gamma m is equal to dry adiabatic lapse rate into 1 minus 0.9 into R. 0.9 is basically the ratio between specific heat constant for dry air divided by specific heat constant for water vapor, and R is the mixing ratio. Now let's consider an air parcel. Consider an air parcel having a mixing ratio Consider an air parcel having a mixing ratio of 22 gram per kilogram. Can you calculate the moisture adiabatic lapse rate for this parcel? So what is the equation for moisture adiabatic lapse rate? Gamma m or MALR is given by minus gamma d into 1 minus 0.9, where R is the mixing ratio. given as 22 gram per kilogram. Yeah. So how much it will be? What will be the value of gamma m? We know the value of gamma d as 9.8 Kelvin per kilometer. So please substitute gamma m will become 9.8. We have to convert it into uh, meter SI unit. So 9.8 into 10 raised to minus 3 Kelvin per meter into 1 minus 0.9 into 22 gram per kilogram. Again, this we need to convert it into kilogram per kilogram. It will become 0.022. How much it will be? Gamma m. Can you calculate and tell me? How much it is coming? The value of gamma m. The value of gamma m will be approximately 9.6 into 10 raised to minus 3 Kelvin per meter or 9.6 Kelvin per. This will be the value of gamma m. So basically from the equation we can see higher the value of mixing ratio, higher will be the difference between dry adiabatic flash rate and moist adiabatic flash rate. So as the value of R is increasing, this difference between, because it is 9.8 into 10 raised to minus 3 into 1 minus some value. So as this value of R is increasing, the difference between dry adiabatic flash rate and moist adiabatic flash rate also increases. So the temperature, that rate at which the temperature reduces in case of a dry air and moist air also. The difference will be more in case of higher value of W. And this mixing ratio, W or R, mixing ratio basically. So the value of mixing ratio is dependent on the geographic location as well. So in case of coastal region, the air over the coastal regions will be having a higher value of mixing ratio, which basically means the difference between DLR and MALR will be higher over coastal regions. So over dry regions, if the value of R is very less, in that case the dry adiabatic lapse rate will be approximately equal to the moist adiabatic lapse rate. Okay, so it has a geographical dependence also. The value of R is having a geographical dependence. Just like that, the difference between dry adiabatic and moist adiabatic lapse rate also is having a difference based on the geographical location that we are considering. Just a second, some issue with the presentation. Yeah, it is coming around minus 9.6 into 10 raised to minus 3. So that is about dry adiabatic lactate and moist adiabatic lactate. Now, so these values we calculated based on a number of assumptions that the dry adiabatic lactate we have calculated based on a number of assumptions. So if we actually measure the lactate of atmosphere using instruments such as radiosonde. Radiosonde, you have seen, it is a large hydrogen or helium balloon which is um, connected to a small instrument box kind of. So as the balloon goes up in the atmosphere, the instruments or sensors which is attached to the balloon will keep on measuring temperature, pressure, etc. So and it will send the values that it is measuring to a receiving station which is in the surface, or uh, to a system which is in the surface. So basically we will get to know what is the temperature as the balloon is going up in the atmosphere, how the temperature at different layers in the atmosphere is reducing. So the value that have been calculated based on measurements such as from radiosonde and all is basically 6.5 Kelvin per kilometer, which is actually less than the theoretical value of 9.8 Kelvin per kilometer. So the observed value or the observed value of lapse rate is generally 6.5 Kelvin per kilometer, whereas theoretically when we calculate the dry adiabatic lapse rate, it is coming to be 9.8 Kelvin. This is generally the environment lapse rate. Sorry. Okay. So just so you know, like this is the actual that we are getting by measurements. So now, so we learned now we know what is dry adiabatic lapse rate, and now we know what is moist adiabatic lapse rate. If some amount of water vapor is present in the air parcel, this will be the lapse rate. Now, what if the parcel is saturated? Now we have another kind of lapse rate, which is saturated adiabatic lapse rate. So we know gamma D or dry adiabatic lapse rate is minus G by CPT, specific heat constant for dry air, and we know gamma M as minus G by CPN, which is specific gas constant for moisture, which we got as minus G by CPD into 1 minus 0.9 or R as a maturation. Now let's find another. So in this case we know the parcel is moist, which means it has water vapor, but it is not saturated, it is unsaturated. Now what will happen if the parcel is saturated? So we will see that. So once the parcel is saturated, the lapse rate is known as saturated adiabatic lapse rate. So for adiabatic processes, the equation of state is basically written as T p raised to minus chi is equal to a constant, where chi is given by R by C. So this is known as a Poisson's equation. This basically comes from the first law of thermodynamics. So now if we take log on both sides, it will become log T is equal to chi into log P. Or and now if we differentiate, we can write dt by T is equal to chi into dt by T. So this is in case of adiabatic case. Now for pseudo adiabatic process, so we know once it is saturated, water vapor, if it goes beyond saturation, water vapor will be formed. It will no longer be adiabatic, it will be pseudo adiabatic. Pseudo adiabatic. case of pseudo adiabatic process, the equation of state becomes same thing, this thing, dt by t will become chi into dt by t minus LV dEs by Cp. So this additional term comes because of saturation condensation those processes. So this additional term comes in pseudo-adiabatic process with respect to the equation for adiabatic case. So dt by t is equal to chi dt by p minus LV dEs by Cp into d. So this is when we include moisture or when the parcel is saturated. This is the equation of state for pseudo-adiabatic process. So we will start from here. We will start from the equation of state. So our purpose is to derive the equation for saturated adiabatic chemistry. So we will start from the equation of state for a pseudo-adiabatic process. So given by dt by t is equal to chi into dt by t minus LV So this term comes because the parcel is saturated or the parcel is moisture saturated. So if we divide this equation, it will be 1 divide equation 1 by dz. If we divide this equation by dz, it will become 1 by t into dt by dz is equal to chi by p into dp by dz minus LV by CPT into DES by dz. So we divided it by dz. We divided the whole equation by dz. Now let's substitute some terms that we know. So the value of chi is basically R by Cp. T we know as rho RT. And we also know dP by dz is equal to minus rho G. Now if we substitute this equation will reduce to 1 by T dt by dz is equal to, we will substitute chi as R by Cp, it will become R by Cp. We will substitute T to rho RT, R by Cp into rho RT. dP by dz we will substitute as minus rho G, minus rho G minus LV by CPT into DES by dz. Now we can try. So we need dt by dz basically, right? So for saturated adiabatic substrate. dt by dz, t we have to take it to the right hand side. So it will become dt by dz is equal to RT by Cp rho RT into minus rho G minus LVT by CPT into DES by dz. Now lot of terms are common. So R will go, T will go, rho will go. Here T is. So it will become dt by dz is equal to what is remaining in the first term. Here everything went, only G and Cp is remaining. So dt by dz is equal to minus G by Cp, and here in the second term it will be minus LV by Cp into DES by dz, minus G by Cp minus LV by G into DES by dz. So if we take G by Cp, which is gamma d as common, dt by dz will become minus G by LV by C. Will be LV by C. Now if we take G by CT common, it will be LV by G into DES by DZ. Or we can write minus gamma D into 1 plus LV, which is the latent heat of vaporization, divided by G into DES by DZ. This is the value of dQ by dZ in case of a saturated air pass. So now we have three different lapse rates. The first one is dry adiabatic lapse rate, which is for dry air, no water vapor, which is given by minus G by C. Then if we have moist adiabatic lapse rate, this is for air parcel that are moist air which has water vapor but it is unsaturated. So in this case it was minus G by Cp into 1 minus 0.9 into mixing ratio R. So it basically depends on the amount of water vapor present in the air parcel. Now the third one is the saturated adiabatic lapse rate, which is saturated air parcel. In case of saturated air parcel, we got it as minus G by Cp into 1 plus LV by G into DES by DZ. So yeah, dry adiabatic lapse rate, moist adiabatic lapse rate, and saturated adiabatic lapse rate. So when we are basically lifting an air parcel, initially the parcel will be unsaturated. So if we lift it adiabatically, it will follow the moist adiabatic lapse rate. Once it will, so we have a moist air parcel. We are lifting it in the atmosphere. Adiabatically at LCL will become saturated. So then, so this it will be following gamma M, which is the moist adiabatic lapse rate. So once it is saturated, it will be following gamma S, or we can write gamma saturated adiabatic lapse rate. So in this case, after this, it will be following this value of lapse rate. So in this case, the value of gamma D, which is the value of dry adiabatic lapse rate, is 9.8, will be greater than moist adiabatic lapse rate. We saw the value is less than gamma D, so it will be gamma M. Then if we calculate the value of saturated adiabatic lapse rate, it will be further lower. So if we calculate, it will come around 6.5 or something. So it will be further lower than the moist adiabatic lapse rate. So the order is dry adiabatic lapse rate is having the highest value. Once it has some moisture, the speed at which it cools further reduces. Once it is saturated, the rate at which the temperature drops further reduces daily. So this is how it varies. Dry adiabatic lapse rate is having the highest value. Adiabatic lapse rate greater than March adiabatic lapse rate greater than saturated adiabatic lapse rate. I hope it is clear. We learned all three. And when it is used, I think it is clear. Now let's see the vertical motion of an air. What are the properties of an air parcel? How it is changing as the parcel is moving up in the vertical motion of an air parcel. This is temperature. This is height. Okay. So now we know the temperature is reducing in the atmosphere. So there will be a temperature profile for the atmosphere, right? As we go up, how the temperature is changing. So this is the temperature profile. Now we have an air parcel which is having the same temperature as that of the atmosphere at the surface. This air parcel is moist, which means it has, consider a moist air parcel which is having a temperature equal to that of the surface temperature. Now this parcel is rising in the atmosphere. Consider it is rising in the atmosphere. The temperature of the parcel will reduce at moist adiabatic lapse rate initially. Now it will eventually reach a point and the parcel will become saturated, right? So what is this level called? This is known as lifting condensation level. So since it is a moist air parcel, till the lifting condensation level, the parcel is moving. The lapse rate of the parcel is given by moist adiabatic lapse rate. Now the parcel has reached LCL. Now the actual temperature of the parcel is equal to the dew point temperature. Parcel is saturated. The parcel is saturated. Now above this, the parcel will be moving in the saturated adiabatic lapse rate, which is again lower than the moist adiabatic lapse. It will be moving like this, saturated adiabatic lapse rate. Even though there will be above LCL, there will be an additional amount of heat that is being supplied to the parcel as well, which is due to the latent heat of condensation. So above that, it will be moving at saturated adiabatic lapse rate. Now after this, at some particular level, so this will be lower than the environmental or the temperature profile of the atmosphere because there is additional amount of heating that is occurring. So at some particular point, the temperature of the parcel will become equal to that. Let the temperature of the parcel be T dash. T dash will become equal to the actual temperature or the atmospheric temperature. That particular layer is known as LFC. LFC is the level of free convection. And above this level, the temperature of the atmosphere keeps on decreasing. But due to condensation, as more and more heat will be produced by the air parcel, eventually the temperature of the parcel will be higher than that of the environment. The temperature of the parcel will start, once the condensation is over, it will start decreasing again. Then again it will meet the lapse rate, environmental lapse rate or temperature profile of the atmosphere at some other point. This is known as LN, level of neutral buoyancy. So this level is basically considered as the top of the thunderstorm cloud level. So above the LNB, the temperature of the atmosphere also starts increasing. It is kind of the top of the troposphere. We can say it is kind of the top of the troposphere. So yeah. So we have three different levels. One is the level of lifting condensation level. First one is the lifting condensation level. At this level, T dash, or the temperature of the air parcel, is still less than the temperature of the atmosphere, but the parcel is saturated. And before LCL, it was moving according to the moisture adiabatic. So after above LCL, condensation will start occurring. So the temperature of the air parcel will, like, there will be one thing is the lapse rate at which the temperature reduced will become saturated adiabatic lapse rate, which is less than the moisture adiabatic lapse rate, and also there will be additional supply of heat to the parcel due to the latent heat of condensation, which is given by which will be used to add to the parcel. So at the second level, which is the level of pre-condension, temperature of the parcel will become equal to that of the temperature of the surroundings. That is level of pre-condension. And the third level is the level of neutral buoyancy. So after level of pre-condension, the temperature of the parcel, if the Z is greater than LFC, once the height is greater than LFC, T dash will be greater than T, which means the air parcel will be having a higher temperature than that of the atmosphere, the surrounding air, which means it can freely move up in the atmosphere. It doesn't need, so till LCL, the air parcel is having a temperature less than the actual temperature. So T dash is less than the actual temperature till LCL. So in that case, till LCL, we need to some external energy is required to lift the air parcel to that particular level because the temperature is lower. So due to some external force, the parcel is actually lifting. So once it reaches level of pre-condensation and the parcel is having a temperature less than that of the surrounding temperature, so it is less buoyant, or it is the buoyancy is, we have to give it some external energy for the parcel to move up. So after LFC, the temperature of the parcel and the temperature of after LFC, the temperature of the parcel will be greater than the surrounding temperature. Then the parcel is basically self-buoyant, which means the parcel does not need any external agent to lift it. It can move up by its own. Since the temperature is higher than that of the surrounding temperature, the parcel is basically self-buoyant above LFC, and the parcel moves up in the atmosphere um, without the help of any external agent. So till here, till LFC, T dash is less than T. So this external agent is required to lift the parcel till LFC. After LFC, T dash, this is the this line shows you the temperature of the parcel. T dash is greater than T. So the parcel is self-buoyant. There is no need of any external agency. This is positive. This area is so this area of the curve is basically known as Sin. CIN. This area of the curve is basically known as K. This is conductively available potential energy. And this area of the curve is known as conductively inhibition energy. So these terms are important when you are dealing with thunderstorm and all those. When you are dealing with thunderstorm clouds or the process of formation of thunderstorm and all those things, these terms comes into play. So just so you know, I just wanted to introduce that positive area of the curve above LFC is known as the conductive available potential energy, and the negative area of the curve below the level of pre-condension is known as till the level of free convection. The air parcel is having a temperature lower than that of the surrounding temperature. So it is not self-burning. We need some external agency or some external source of energy is required for the parcel to rise up till level of free convection. After LFC, what happens is that the temperature of the parcel will become greater than that of the surrounding temperature, and the parcel will rise on its own. No external energy is required to be provided to the parcel to rise up in the atmosphere. So that area is known as convective available potential energy, and this area is known as convective inhalation energy. And the three layers in the atmosphere, three levels in the atmosphere, is level of lifting condensation level, the level at which the parcel will acquire, the level at which the parcel is acquiring saturation is known as lifting condensation level. Above lifting condensation level, the parcel will start condensing, and an additional supply of energy in the form of latent heat of condensation will be supplied to the parcel. The second level is the level of free convection, above which the parcel will be having a temperature greater than that of the surrounding temperature. The parcel is self-buoyant. And the third one is the level of neutral buoyancy, where the temperature of the parcel will again go below that of the surrounding temperature. And this is basically considered as the top of the thunderstorm cloud. So this will be having an, so if you take a thunderstorm cloud, this will be the base of the cloud, and there will be thunderstorm, like vertically developing clouds you would have seen when during pre-monsoon time and all. So it will be like this. So this will be generally the lifting condensation level, and this is generally the LMB. The thunderstorm clouds acquires the shape of an angle at the level of neutral buoyancy, since it can't go beyond this level. So this maybe because of the top of the troposphere. Above this, the temperature starts increasing in the atmosphere. So only till this point, the thunderstorm clouds can grow. So that is lifting condensation level. This will generally be the base of the cloud. This will be the top. You would have seen these big thunderstorm clouds during pre-monsoon time. Okay. Now, as I told you, before level of lifting condensation level, the air parcel can't raise by its own. So some external agencies provide the energy of the provide the energy for the parcel to rise in the atmosphere. So there are different lifting mechanisms that are present in the atmosphere, which basically lifts the air parcels present. I'll just introduce you different lifting mechanisms that are generally seen in the atmosphere. So the first one is convergence happening in the atmosphere. So suppose if there is a low pressure surface that is present, suppose there is a low pressure system that is present in the surface, what happens is that the surrounding, since it is low pressure, the surrounding will be at a higher pressure. So the air parcel starts to move towards this low pressure. Air parcel starts to move towards the low pressure from the surrounding high pressure region, and there will be a large amount of air in this region will be higher due to this convergence that is happening at the lower layers. So what happens is that this air parcels, whatever is present in the lower surface, will begin to move up. It will start moving up. So this convergence is happening in a low pressure region. So a lot of air parcels will be present here. So it will slowly start moving up. So when there is a convergence, that is lower level convergence, generally lead to the forming this lifting of air parcels from the surface, because all air from the surrounding will be coming towards this low pressure, and so it will accumulate kind of in those regions. So it will eventually lift up in that. So convergence systems that is present in the surface will lead to lifting of the air parcels. Cyclone is basically a low pressure system where we can see this large amount of air coming together and eventually lifting and forming a large amount of one example, which is convergence. This is one form of lifting mechanism. Second one is the orographic lifting. Orographic lifting basically means suppose there is a mountain, hill, or something present in the atmosphere. This is the surface. We have a mountain is there, so air is flowing like this. So when it comes into, this is like this, air is flowing. When it comes in contact with this, there is a hindrance in the path of this air. So what happens is once it hits it, it will start moving up because it can't move like in straight lines anymore. So it will start moving up. So this is orographic lifting. So second lifting mechanism that is present in the atmosphere is generally orographic lifting. So orographic lifting is generally the reason for our monsoon systems. During monsoon and all, we generally get rainfall. That is June, July, August, September period. The monsoon time that we are getting rainfall is mostly due to orographic lifting. So if you look at the regions that are receiving very high rainfall during monsoon, that is mostly over the Western Ghats region, which is having this. So as the monsoon from the Arabian Sea, the regions that receive very high amount of monsoon, suppose this is India, so this is our Arabian Sea. We have Western Ghats over here. So as the southwesterly monsoon winds are coming, it will be lifted by the Western Ghats, and they will receive a large amount of rainfall is received over this region. And then if we look at the regions which receive very high amount of rainfall is the northeast region. So they also Himalayas and all those. So there also, due to the presence of the mountains, the wind that is coming towards the mountain is basically being lifted by these mountains. So that is basically orographic lifting. And the third one is convergent convective system. Suppose there is a lower, if there is some anomalous heating happening over a particular surface, like this urban region and all, so those regions will be due to some reason, some regions are having such a higher temperature compared to the surroundings. So in that case also, if some region is having a higher surface temperature, the air over those regions will also be having a higher temperature. So parcels will since it is at a higher temperature compared to surroundings, the parcel will basically start to rise in the atmosphere due to the high buoyancy or lower density. So those kind of anomalous regions where this anomalous heating is happening result in convective system. Convection will happen over those regions. So that is the third one. And the fourth one is basically frontal systems. Frontal systems mean suppose there is a layer of cold or some cold air is coming from one region and warm air is coming from another region. At some particular point, these two air parcels will eventually meet with each other. So when this cold and warm air will meet, so cold air is having a lower temperature and warm air is having a high temperature. What happens is that the warm air will eventually rise. It can't move. There is a hindrance that is caused due to this cold. So there is a hindrance that is close to this cold air moving. So once this warm air touches it, it can't move like this. So it will start moving up like this, and eventually lead to the formation of clouds. So these are known as fronts. So if warm and cold air comes close together, two air parcels having different temperature comes closer together, the warmer air parcel will rise above the cold air parcel. So that is basically fronts. So these fronts are generally seen in mid latitudes. So over the mid latitudes, their weather systems are mostly determined by this frontal systems. So these three are the four different lifting mechanisms. So as I said, initially we need to give some external energy due to some lifting mechanism only. The air parcels are being lifted till the level of lifting condensation level, and above that the parcels can and above lifting condensation levels, condensation will start occurring. It will eventually reach the level of free convection. And above level of free convection, the parcel can rise on its own. Okay. Yeah. So that is, I think I will wind up here. I think the things that I have told is clear. If you have any doubt, you can ask, or we will meet in the next week. Okay. Thank you. Thank you. Yeah. Happy Women's Day. Thank you. So, Soumya, may I know what you are exactly doing? Uh, where are you studying actually? Okay, MSc first year. Okay. Which MSc, which physics, which course actually? Central University of Karnataka. MSc in physics you are doing? Okay, okay, okay. Thank you. Okay.